UTME is around the corner, and that's why we will not waste time. We have to start revision immediately. Welcome to 2026 UTME revision class on physics. Today we are looking at temperature and its measurement. In part 1 we looked at the meaning of temperature, we dwell on that, and we looked at various temperature scales and the relationship between various temperature scales. Remember, we also considered the fixed points of a thermometer. So today, our business, we are going to look at thermometric substances. In our revision series, we usually pick a question and then we dwell on that aspect of the topic before we now answer the question. And the question we have here is a question that is related to thermometric substances. So we are going to look at thermometric substances. So we look at thermometric substances. So what do we mean by a thermometric substance? What is a thermometric substance? A thermometric substance is any material that its physical property changes with temperature. So thermometric substance a thermometric substance is any material that its physical property changes with temperature. So because their physical properties usually change with with temperature, we use them in temperature measurement. Therefore, they can be used. Therefore, a thermometric substance can be used in temperature measurement. And we know why we can use them in temperature measurement, because their physical properties usually do change with temperature changes. So any substance that its physical property will change as temperature changes, we call such a material. Any material that its temperature will bring about a change in its physical property, such material is said to be a thermometric substance. Yeah. So every thermometric substance will have at least one physical property that will vary or that will change with temperature. We have so many thermometric substances. A liquid can be a thermometric substance. Gas can also serve as a thermometric substance. That means we can use a physical property of a liquid to measure temperature. We can use a physical property of a gas to measure temperature. But the important thing is that that particular physical property that will be used will change with temperature changes. Okay. Then we also have resistant wire, commonly platinum wire or electrical wire. You can say electrical wire is another substance that can serve as a thermometric substance. So all we need to know is the physical property that is peculiar to each of these substances that we refer to as thermometric substances. For example, liquid. What physical property of a liquid will change with temperature change? What physical property of a gas will change with temperature change? And what physical property of an electrical wire will change with temperature change? That particular physical property of any of these substances that will change with temperature change, that's the property that we use as basis of temperature measurement. For a liquid, it is the length of the liquid column. So it deals with expansion in liquid. If you have a liquid column, if you have a liquid in a vessel or a capillary tube, this is a liquid inside this capillary tube. Now, if temperature begins to change, the liquid will either rise or do what? Or drop. So the length of the liquid column becomes the what? That's based on the expansion of the liquid, becomes the physical property that we will look at and use it to measure what? To measure temperature. So for liquid, when you are using a liquid as a thermometric substance, the physical property that will change is the length of the liquid in a capillary tube. So the length of the liquid is the physical property. If you start heating this tube now, you'll notice that the length of the liquid will start increasing because of increase in temperature. So the length of the liquid will change because temperature is changing. If you now begin to withdraw heat, in other words, you are decreasing the temperature, you will notice that the length of the liquid will begin to do what? Drop. So liquid in glass thermometers use what? Liquid as what? Thermometric what? Substance. As thermometric substance. Then we look at gas. The physical property of gas that we consider as basis of temperature measurement is the what? Is the pressure of the gas. Remember, we say in liquid it is with the expansion of the liquid in a tube, and that expansion we can easily measure it by considering the length of the liquid as it rises or what? Or fall. But for gas, we look at the pressure, the change in the pressure of a gas as temperature changes. We use it as basis for temperature measurement. So the physical property in a gas that we consider as basis for temperature measurement is the pressure, because pressure changes with what? With temperature. Then in electrical wire, the physical property we consider is resistance of the wire. We know that the resistance of a wire changes when there is a change in what? In temperature. So a change in temperature will bring about a change in the what? In the resistance of the wire. So these are the physical properties that we have to consider for these thermometric substances. Yeah. Now you know that there are other forms of measurement of temperature. You can also measure temperature based on change in the EMF. That's where the thermocouple comes in. Yes, the thermocouple. You can use the EMF, variation of EMF or variation of current with what? Temperature. In that case, you use a type of thermometer we call the thermocouple. The thermocouple. Then we can also measure temperature based on light intensity, where we use a device we call the optical pyrometer. The optical pyrometer. The optical pyrometer. So when you are looking at temperature measurement from the angle of light, you use the thermometer we call the optical pyrometer. This one works with light, and that light is usually compared to your filament lamp. You know the filament lamp? The filament lamp, your normal bulb, yes, we compare that light to it. So the change in light intensity can also be used as basis, but that is used in optical pyrometer. Optical pyrometer is a very important type of thermometer because it's used in measuring very high temperature. So when you have a system that usually generates high temperature, optical pyrometer will be the best thermometer for it. But the common thermometer that we look at are the liquid in glass thermometer, the constant gas volume thermometer, and the resistance thermometer. Yeah, based on the three thermometric substances that we looked at. We say a liquid can be a thermometric substance, a gas can be a thermometric substance, and the what? And a resistance wire can be what? A thermometric substance. That's electrical wire, can be a thermometric substance. And based on that, we have types. We have types of what? Types of thermometer. The types of thermometer will now be liquid in glass thermometer, constant gas volume thermometer, and what? And resistance what? Thermometer. Resistance thermometer. So in liquid in glass thermometer, liquid in glass thermometer, The thermometric substance here is a liquid. So a liquid is used as thermometric substance. A liquid is used as thermometric substance in liquid and glass world thermometer. So a liquid is used as what? Thermometric substance in liquid in glass thermometer. So we use a liquid as well, thermometric substance. Now the liquid we are going to use in liquid in glass thermometer, remember we said liquid in glass thermometer is one of the types of thermometer based on the word, on the thermometric substance. We also have gas thermometer, that's the constant gas volume thermometer, and we have resistance thermometer. In liquid in glass thermometer, the liquid that we are going to use must have some properties. What are these properties? The liquid must be opaque. The liquid needs to be opaque so that it can easily be read for readability. It has to be opaque. It must be a good conductor of heat, so it must have high thermal conductivity. High thermal conductivity must be high, must be a good conductor of heat. Then such a liquid should not wet glass, wet glass. Any liquid we are going to use. So properties of a thermometric liquid. Properties of a thermometric liquid. One, it has to be opaque. Two, it must have a high thermal conductivity, meaning it must be able to conduct what? Conduct heat. Three, it should not wet glass like water. It should have regular expansion. It shouldn't behave like water. Water has an expansion we call anomalous expansion of water. The expansion of water is anomalous, it's irregular, because we know that when you heat water from a temperature of 0 degrees to what? To 4 degrees, water contracts. So if instead of application of heat bringing about expansion, the application of heat brings about contraction in water until you get to a temperature of 4 degrees where it experiences the least volume, that is the highest contraction. And after 4 degrees, it will start expanding again. Because of that behavior, we say that water has anomalous expansion. So that's why water, one of the reasons why we cannot use water for as a thermometric substance or as a thermometric liquid is because water has irregular expansion. So any substance that will be used as a thermometric liquid must have these properties. One, it must be opaque, high thermal conductivity, it should not wet glass, regular expansion, it should have such substance must have high boiling point and low melting point or low freezing point, freezing or melting point. It should have high boiling point and low freezing point. It should also have high expansion. It should be able to expand properly. It should be able to expand properly. So these are some of the properties of what? Of a thermometric liquid. A thermometric liquid. Now the liquid that we usually consider as the best thermometric liquid is usually mercury, because mercury has most of these properties. Mercury is opaque. It has high thermal conductivity. It doesn't wet glass. It has regular expansion, although it doesn't expand much as alcohol. The expansion in alcohol is about 6 times that of mercury. But mercury has high boiling point, although it has a high melting point. It's supposed to have a very low melting point or very low freezing point. So alcohol has a lower melting point or lower freezing point than mercury. So in all this, alcohol beats mercury in terms of expansion, the high expansion, and also in terms of in terms of having a very low freezing or melting point. So the freezing point of alcohol or melting point of alcohol is lower than that of mercury. So that's where it beats mercury. And also in terms of expansion, we have said that alcohol expand about 6 times the expansion we have in what? In mercury. But others, mercury takes what? Upper hand. Alcohol is transparent, it's not opaque. So if you are going to use alcohol as a thermometric substance, you need to color it. You have to color it. The thermal conductivity of mercury is greater than that of what? Alcohol. And the question we have on the board is a typical question that concerns this, right? Comparing the thermometric properties of what? Of alcohol with that of what? Mercury. So let's quickly answer this so that we can look at other types of what? Thermometer, and see if we can pick a question to do 1 or 2 calculations as it concerns the types of what? Thermometer. Okay, quickly. They say, which of the following are true about the advantages of mercury over alcohol as thermometric what? Liquid? 1. Mercury is opaque. That's an advantage, right? With higher thermal conductivity. I just said that the thermal conductivity of mercury is greater than that of alcohol, so we think this good. This is an advantage of mercury. Mercury has higher thermal expansivity, but we have said that alcohol expands 6 times that of mercury, so that's not correct. So this has nullified this. Then mercury has higher boiling point. That's correct. It has higher boiling point and does not wet glass. That's correct. It's an advantage over alcohol. It expands uniformly. That's correct. Lower freezing point. That's not correct. Mercury has uniform expansion. Has lower freezing point. No, the freezing point of alcohol is lower than that of what? Mercury. So we'll cancel that. Has higher specific heat capacity. That's not correct. The specific capacity of mercury is not what? It's not higher, and mercury is not also cheaper than alcohol. So that's cancelled it. So the advantages that we have here are I and I. So we go to the option. Where do we have I and I? So B is the correct answer to this question. B is the correct answer to this question. This is the type of question that UTME, that JAMB will always ask in their UTME exams. Okay, so now let's continue with this. So having looked at the properties of thermometric liquid, we have just used it to answer this particular question. You can search your past questions and then check if there are questions on thermometric properties of thermometric liquids and see whether you can actually answer the questions. I know you can answer them based on what we have done. Okay, we are still on this business of temperature and its measurement. Now, in liquid in glass thermometer, we say that the length of the liquid in the thermometer, right, changes with what? Temperature. The length of the liquid changes. So every length of a liquid will correspond to a particular what? Temperature. Yes, every length of a liquid will correspond to a particular temperature. So as temperature changes, the length of the liquid is doing what? Changing. So if you are increasing temperature, the length of the liquid will do what? Increase. So how can we now use this to determine temperature? Now you remember that in the first video we looked at fixed point, the upper fixed point and the lower fixed point. Now let's assume that I have this as my length, right? Here is length, and then I have this, right? And here is my thermometer or temperature. Let me say temperature. So here is my temperature. Now let the temperature at the bottom here, the temperature here be the lower fixed point, which is 0 degrees, right? Now let the temperature here be the upper fixed point, which is what? 100 degrees. We know that the lower fixed point in terms of Celsius or centigrade scale is 0. The upper fixed point is what? 100. Remember that we said that lower fixed point, lower fixed point is the same thing as what? Ice point. And then our upper fixed point is the same thing as what? Steam point or boiling point. We don't want to call it steam point, it's boiling point. Ice point, melting point, freezing point is the same thing. So ice point, freezing point, melting point means what? Lower fixed point. Steam point, boiling point means what? Upper fixed point. Okay. So now let the length that correspond with the lower fixed point, let me call it L0. That's the length of the liquid, right, at lower fixed point. And let L100 be the length of the liquid at upper fixed point. Now, if I have any temperature that I want to measure, there should also be a length. So let me call it that length, L theta. L theta. Now, if I compare this and this, I can establish an expression where I will now have that theta over what? 100 is equal to L theta minus L0 all over L100 minus L0. I can use this relationship to find temperature for any given what? Length, or to find the length of the mercury column for any given what? Temperature. So in this case now, we can see that L0 is length at what? Ice point. Length of the liquid that is used in liquid in glass thermometer at ice point. L100 is the length at what? Steam point. That's lower fixed point now. Remember, ice point is lower fixed point and steam point is the what? Upper fixed point. As steam point is what? Upper fixed what? Point. Then L theta now is length at any other temperature, right? The temperature that is not the upper or that is the upper fixed point or the lower fixed point. So length of liquid at any other what? Other temperature. At any other temperature. That's the length of the liquid at any other temperature. So L0 length at ice point or the upper fixed point, the length at lower fixed point. L100 length at what? Upper fixed point, or length at steam point, or length at boiling point. Remember, I explained this here. Lower fixed point means ice point. It also means freezing point. It also means melting point. Upper fixed point means steam point. It also means boiling what? Boiling point. Okay. So that's for what? The liquid in glass thermometer. Now, this is a revision. That's why we are trying to rush revision class. Now, we can also extend this. If you are now dealing with resistant thermometer, so you are dealing with resistance thermometer. We can apply the similar principle here in resistant thermometer, because temperature changes with what? Resistance, or resistance changes with what? Temperature. A change in the what? Temperature will result to a change in the what? Resistance. So in that case, if we look at, we are going to have a similar expression here, that theta over 100 will give me R theta minus R0 all upon R100 minus R0. So where theta is the temperature of interest, the temperature we are looking for at any temperature, then we now see that R0 will be resistance at what? Ice point. Remember, ice point is what? Lower fixed point. And R100 is what? Resistance at what? Steam point. At steam point. And then R theta is resistance at any other what? Temperature. When we say any other temperature, it means any other temperature theta, that is neither this or this. So any other temperature theta. So where theta now is any other what? Temperature. So you notice that this now can be written in terms of what? Resistance now. Instead of length, we have resistance. And we can still do the same for gas thermometer, the constant gas volume thermometer. Gas thermometer. In gas thermometer, a change in temperature will bring about a change in pressure. So we'll have a similar expression that theta over 100 will be pressure at any temperature minus pressure at ice point, pressure at steam point minus pressure at what? Ice point. So you see, the whole equations are the same. If I know this, for resistance, all I need to do is to change the L to R. For pressure, all I need to change is the what? The L to what? P. And they have the same similar meaning. Similar meaning. It's just a property that will change. So I can now say that P naught is pressure at what? Ice point, right? And P100 is what? Pressure at what? Steam point. That's upper fist point. And then we can now say that P theta is what? Pressure at any other what? Other temperature. At any other temperature. Then we know that theta, we have defined theta as any other what? Temperature. That's this theta. So this can also, for pressure, that's for gas thermometer. In gas thermometer, it is the pressure that will change with what? With temperature, not the volume. That's why we call it constant gas volume, or constant gas volume or thermometer. Yeah, constant gas volume thermometer, because the volume is constant. Temperature is changing with what? With pressure. Okay. Wow. So these three expressions are very important. This, the one I just clicked on, liquid in glass, and that of resistance thermometer. So quickly, we can, I believe you have made note of this. So let's take maybe the question to illustrate this, and then I will now leave you to look for more questions in the past question. If there is anyone you couldn't solve, you can just drop it in the comment section, then we'll look at it together. So let's take a question, maybe one or two questions on this. One or two questions on this. Maybe I will now give one that you are going to solve later. Okay? So let's look at this together. So I can look at, we have looked at question 1 and 2. Question 1 in the first video, question 2 in this video. So let this become our question 3. They say the lower fixed point, which is the ice point, corresponds to a length of 20 millimeter on the stem of a thermometer, while the upper fixed point corresponds to 160 millimeter. The temperature that corresponds to a length of 48 millimeter is, they gave us option A, we have 20.0 degrees Celsius, B 30.0 degrees Celsius, C 41.7 degrees Celsius, and D 50.0 degrees Celsius. Okay, for clarity, we have to solve it on this part of the board quickly. So let's look at this question together. So for us to solve, we need to bring out the parameters given in the equation. So solution to this. The lower fixed point corresponds to a length of what? 20 millimeters. So the length at lower fixed point. Okay, let's list our parameters here. the length at lower fixed point, the symbol is LO. LO sub 0 is what? 20 millimeter. And they say why the what? Upper fixed point, that's LO 100, corresponds to what? 160 what? Millimeter. And they said the temperature, what temperature now? We are looking for theta. We correspond to a length of 48 millimeter. So length of theta 48 millimeter. So what temperature? We have this length. Lower fixed point has this length. Upper fixed point has this length. What temperature theta? We have this length. That's what the question is saying. So if we invoke our expression, you remember that beautiful formula that theta over 100 is equal to L theta minus L naught, all upon what? L 100 minus L naught. So we're looking for theta, so we leave it as theta over 100. What's L theta? 48. So 48 minus what? Minus 20. That's what we have there as the length of the lower fixed point. And the what? 160 minus 20. Because the upper fixed point length is 160. So that will give me 48 minus this is what? 28. Divided by 160 minus this will give me what? 140. Was theta over 100. We can actually break this down. I know that 14 can divide here. Even 28 can still divide here. 28 can divide itself 1. When 28 divides this, we are going to have 5. Because 5 times 28 is 140. So 28 here 1, 28 here is 5. Right? If you clear the fraction, you have that 5 theta is equal to 100 times 1 here, 100. So theta becomes 100 over 5. And theta will give us what? 20. In the option we have what? 20.0, which is still 20 degrees Celsius. Wow, that's beautiful. That's beautiful. So I will not leave you empty-handed. They just took light now. So what will I do? We are still going to continue, but I'll have to give you a question that you will solve, and I want you to leave the answer in the comment section. Just solve the question and leave the answer in the comment section. So let's look at this as a takeaway question. So your takeaway question. Let's see what we are going to do based on what we have done so far. A platinum resistance thermometer. A platinum resistance thermometer has resistance of 5.25 ohms and 9.75 ohms at 0 degrees. That you remember that 0 degrees is lower fixed point, you have to remember that. And 100 degrees Celsius, remember that is the upper fixed point. Respectively. You know why they are saying respectively? Okay. When the resistance is 8.25 ohms, the temperature is, let's take the options: A, 63.6 degrees Celsius, B, 66.7 degrees Celsius, C, we have 75.0 degrees Celsius, and D, we have 84.6 degrees Celsius. All right. You are expected to solve this question, and I'm going to see you in part 3. In part 3, we will be leaving temperature and its measurement. We will be moving straight to heat and its measurement. We'll look at effect of heat. But remember, you need to study. If you are preparing for UTME, please study about clinical thermometer. know the features of clinical thermometer. Remember, one of the features of clinical thermometer is that it doesn't have wide range of what? Temperature, because we know why. The body temperature is around 35 to what? 37 degrees. So the clinical thermometer does not require wide range. The temperature range should not be getting to 100, 200, because what it's measuring is just within 35 to 37. So it doesn't have wide range of what? Temperature. All right, we're going to see in the next class, and in that class you cannot afford to miss it, because I will be introducing heat. Yes, I will be introducing heat. We'll be looking at revision on heat. Very important as far as UTME is concerned. We'll look at expansion, linear expansion, area expansion, cubicle expansion. We leave that and move to other aspects of heat. We look at heat capacity, specific capacity. We look at latent heat, specific latent heat, and we look at all the calculations that are involved, especially in heat capacity and also in latent heat. You cannot afford to miss that particular class. Remember, solve this question, leave the answer in the comment section. I will see you in part 3 of this revision. Remember, we are looking at thermal physics, and we started with temperature and its measurement. If you are still finding any aspect of temperature difficult, you can let me know. Meanwhile, I have a full video on temperature and its measurement. Remember, this is a revision video. If you desire, I can still forward these videos to you. But why we are doing revision is because we know time for UTME 2026 is very short now. We don't have enough time for full classes now. See you in my next video.